the big picture of dynamics for rigid bodies. I mean, it's succinct, so it's not a very big picture. I guess it's dynamics of rigid bodies. And we've got force affects velocity, which affects position. This, you could think of this as the translational dynamics. And then we have the rotational dynamics. And instead of force, there's moment or torque. I'll use them interchangeably. That affects not velocity, but angular velocity, which affects either attitude or we'd call it orientation. And then this gets divided into the velocity affecting position, angular velocity affecting orientation. This would be the subject of kinematics. Kinematics is just describing the position and orientation and how they're changing in time. So taking derivatives and things. The other part would be, some people refer to this part, how force and moment affect the velocity and angular velocity. They'll call that kinetics. To me, that sounds too much like kinematics. So I would just rather call that dynamics. Some people refer to this whole big picture as dynamics. So I'd say this is what dynamics is when we're talking about particles and rigid bodies. It is the F equals ma and all of its derived things. So that's a big picture. How are we going to get there? So overview of how we will get there. We will start with single particle. So we'll have an inertial origin, and then a single particle that's moving around, and then go to multi-particle systems. So in that case, we'll have multiple particles. I draw them this way, but maybe they're interacting by forces. If you have a bunch of particles and they do not move with respect to each other, so if they're somehow rigidly attached, I think of those pictures from chemistry where you've got the balls attached by rods. So if we have particles and we sort of freeze them by having them rigidly attached, that would be kind of imposing rigidity, but nature does that for us. So rigidity means that now the particles that thought they were on their own are all kind of rigidly attached. So these lines connecting them are fixed. They can't move with respect to each other. The only relative type of motion in this case would be rotation. So that means you would attach a frame to this set of particles. And that would be, once you've got particles attached rigidly, then this is it's like a particle rigid body, a Tinker Toy rigid body, if you remember Tinker Toys, if anybody does. Before that, multi-particle systems could be squishy, but when you've imposed rigidity, you don't get squishiness anymore. I mean, things more than just squishy. I mean, like that's the subject of continuum mechanics. Then when we go from, particles that are rigidly attached and then say, no, let's, instead of thinking of a discrete mass distribution, we go to a continuous mass distribution. Then that takes us to the world of rigid bodies. So now we've got my favorite shape, rectangle thing, to which I have attached a rigid frame. I can find the right orientation. And now the dynamics of this continuous mass distribution. The kinematics is the same as the kinematics of the frame. So describing how the frame is oriented and how that orientation is changing with time is the subject of kinematics. And then how forces, which then become moments, applied to a rigid body, would say, how does that angular velocity change with time? So we've got a continuous mass distribution, still have the idea of a frame attached, body fixed frame that is moving. Mostly the hard part will be how the orientation or attitude is changing with respect to an inertial frame. So how those B unit vectors are changing with respect to the N unit vectors. And let's be a rigid body. and rigid body dynamics. So there'll be something called Euler's equation. It's probably more accurately called Euler's rotational dynamics equation, because there's lots of things called Euler's equation running around. Just Google it for rotational dynamics. That describes how the attitude is changing, and then how this, the path is changing would be given by something that looks like Newton's law, but it's somehow technically not, but we'd call it Newton's. And so together, they are the Newton-Euler approach for describing a rigid body approach. That's no. Okay, so that's the big picture. And it's good to see the steps. Some people just like dive into the rigid body. It's good to see the steps, because you will probably eventually deal with things that are multiple rigid bodies. The simplest satellite, if it has solar panels, it's going to have moving parts that are rotating with respect to it. So that means you got to deal with multiple frames. So most things are not really rigid bodies. If they have moving parts, they're not going to move exactly as a rigid thing. And so knowing how, if you have something that's mostly rigid, but you got some moving part, how does that affect it? That's going to be related to the control part, because we have a satellite, we want it to point in a certain direction. So how do we move it? How do we respond to the environment disturbances, or just sort of redirect to go point in a new direction, or shoot lasers at California, if you know what I'm talking about. All right, California doesn't need lasers, it's got enough problems. So Newton's laws. So as if you have not seen Newton's laws, I will give you an introduction to Newton's laws. I like to skip the first one because I think like it's implied in the second one. So, okay, if something's out in space and there's no force acting on it, it moves in a straight line with a constant speed. I don't even know why that had to be a law. Okay, they only hold in an inertial frame. Inertial frame, which we'll usually write this as an N frame, and we'll usually give it an origin. And fancy N, look at that fancy N. Oh, N1, N2, N3. So we've got some unit vectors that describe this. We usually think of this frame as fixed, but technically an inertial frame can move with constant speed in a constant direction, so constant velocity frames. So if we're looking at a particle, here's a particle. I don't know if we should call it P or M or what, but let's just say, yeah, I'll say P. Then the main thing we care about is this. How is the position? The position would be, we could write it multiple ways, like vector from O to P, or maybe we write it, some books will write it just position of P, or position of P with respect to O. As long as it's clear what we're talking about, then we're good to go. This point is going to, it has a mass, right? It has a mass. We're talking about particles. This is going to move. So there's going to be some inertial velocity. Let's write it that way. Velocity is r dot. And Newton's laws come in saying, how does v dot change with time? But it does it through a particular approach. We're going to give an anatomy of Newton's second law, what he called his second law. And when I say Newton's laws, I usually just mean Newton's second law. So it's kind of a misnomer. But we would say, all right, there is maybe we'll write it this way. There's a force, F, acting on P, okay? This is well, I'll just write the whole thing first. F equals the derivative with respect to this inertial frame of the linear momentum with respect to that inertial frame of P with respect to O. And often we'll skip some of these superscripts and subscripts because we know what's going on. So what does this say? F is let me put little things, F. This is the force, right? It is, what we're writing here is the sum of all forces that are acting on the particle P. Like, where's the mass? What's going on? This is the linear momentum of particle P. And what is that? That would be the linear momentum of particle P with respect to O is the mass of the particle times the inertial velocity. Maybe I'll put a little, no, not an I, we're doing N. M times R dot. So it's M inertial derivative of R P O. Okay. So why do I write it this way? To take into account the possibility that mass might be changing, which ends up being important for anything in space. But usually, right, if we assume M is constant, then we get that F equals mass times, let's call it R double dot, mass times acceleration. So this thing would be the derivative of the point P with respect to the inertial origin O. Okay, so that's the usual way you see it, and sometimes we drop the P and just say F, just F. It's total force. Okay. M, right? M is the mass of the particle. And yeah, this thing is the inertial acceleration. And that's the where you can use the transport theorem. And that's the part that most people, it's taking derivatives with respect to a frame, even though you might have other intermediate frames. That is the main thing that trips people up in doing any kind of dynamics. And that's why I like to try to be very careful about it and give you plenty of practice on it. Because, as I've said, if you can do it for particles with rotating frames, then when we move to rigid bodies, it'll be a piece of cake. Piece of cake. All right. So that's the anatomy of Newton's second law. Is there anything we have not explained? Well, there's this vector derivative, but you know what that is, right? It's the derivative with respect to an inertial frame. Yeah, so that's my interpretation of Newton's second law. So Newton did have his third law. I guess this is where we'll end. Let me write my inertial frame. And I'm not going to give everything. Here is particle 1. I'll call that M1. And then here's particle 2. Maybe I'll make this a big particle. Particles are just points. What makes a particle a particle? It has no physical extent. It is just a mathematical point. So it's an idealization. So this would be M2. And if we were to draw vectors to each of these, this is location of particle 1, location of particle 2. So you might say, Newton's third law assumes that there's more than one particle in the universe. Otherwise, it'd be kind of pointless. And then there is the vector between 1 and 2. R1, 2 equals R2 minus R1. We haven't even gotten to what that third law is. That third law says that if a mass M1 is exerting a force on particle or mass M2, we'll call that force. So force F21 is the force on M2 due to M1, which means it's over here, F21. Then F12, force on M1 due to M2. Newton's third law says that these are equal and opposite. Newton's third law. And he put it in the way that everyone knows, equal and opposite reactions. Now, you might be thinking, hold on, I know other ways I could have drawn this and they're equal and opposite. Like, why can't I do this? F12, and this is F21. Those are equal and opposite. Yeah, well, Newton did not specify, but it's kind of assumed that the only real forces to which this applies is forces along the line connecting the 2 points. And that's why we draw it this way. So we think of F1, 2 is parallel to R1, 2, and same, F2, 1, parallel to R1, 2. So the line connecting them. And that's how we'll be thinking of that. All right, so we will begin more in earnest on dynamics of single particles. So begin looking at chapter 2, the first few sections